Now I'm going to talk about some of the technical aspects of this project. Again, this is a motion replicator. Basically, the user manipulates a target point over here in three-dimensional space by these strings. And the location of this target point is mimicked and replicated by the arm over here. So some of the electrical components of this project, the first of which is the Arduino Uno, which is the microcontroller which serves as the central hub for all of the analogs and digital signals generated by and or used by the electrical parts of this project. Over in the sensing stage, we have the target point, which is tracked by these three multi-rotation potentiometers in blue. They vary in resistance between 0 and 10 kilo ohms. Early in the project, I found that these potentiometers really like to take on values that hover in between two numbers, and this noise really tended to make the arm to dance around schizophrenically. So in order to ameliorate this effect, I implemented a low-pass filter in the code, which made the signals coming from these pots a lot cleaner, and that made the arm's movements a lot more smooth and controlled. As far as the math behind all of this, the target point location as well as the servo angles are calculated by basically sphere intersection math. Over here in the sensing stage, these three string lengths, which are known, are the radii of three spheres which intersect at a point that we are interested in. And this location is calculated on the Arduino and gives a XYZ coordinate in Cartesian, which is then translated into three angles which have to be taken on by these servos. Actually, very similar math is done to find these three angles, but instead of the strings being the radii, now it's these arm lengths, which are the sphere radii. Finally, these three servos are controlled by pulse width modulation, the signals of which, again, are generated by the Arduino, and these servos are powered by this collection of AA batteries. I also found that when I tried to power both halves of the project just from the Arduino, the arm became very, very jittery. So to make that go away, I simply separated the power supplies, and now the servos are powered by these separate batteries, and the jitteriness went away. Let's talk about some of the mechanical components of this project. We'll start with the sensing stage. Now these strings are wrapped around timing belt pulleys, which are then screwed onto the shaft of these rotational potentiometers. As you can see, there are rubber bands glued onto the surface of the timing belt pulleys, and this is to maximize the friction between the string and the pulley to make sure that they rotate together. The potentiometers themselves are multi-rotation. I bought them especially for that purpose, and they rotate up to 10 laps, which gives the strings enough freedom of length. The strings are actually just from retractable lanyards, the kind that you can clip to your breast pocket, and they'll retract after you pull your ID badge to a card reader. And I wanted them to be retractable so that you had to force the target point to a certain location, and if you weren't forcing it, it would return to a default position. Now, if you'll notice, the string origins are here at these drilled holes, and these holes lie along the vertices of an equilateral triangle, and that made the math just a little bit easier to calculate. And actually, the string origins also lie along the x and y axes of a coordinate system which I used for convention. The coordinate system has an origin which is right here, in between these two string origins, and the positive x-axis is in this direction, and the y-axis is in this direction, and the z is upward. Now let's look at the arm stage. The white plastic that you see here is 3D printed ABS plastic, and the clear plastic below is simply 1/8 inch polycarbonate. Now, because the arm has multiple parts that need to rotate freely, I designed the shafts and holes to have a 0.4 millimeter clearance. And this clearance actually worked really well, even after the 3D printing process, to allow for free rotation without too much slop. Now, you'll notice the lower arm here has an I-beam shape, and that was in anticipation of a lot of tension on the belt on this side. But actually, as you can see, I ended up having nearly no tension at all, so in the end the I-beam was not really necessary. The first time I designed these 3D printed parts, I had a lot of sharp right angles, and this caused a lot of issues when we were releasing the parts from their support structures. A lot of pieces just kept breaking away because the interfaces were so weak. So the second run, I added 3 millimeter radius fillets everywhere that I could to make things a little bit stronger, and actually that was very successful at making all of the parts a lot less breakable. Now, this rubber band here transfers the angle from this lower servo to the upper arm, which serves as the pointer. And you might be wondering why I didn't use an actual timing belt pulley or something a little more proper than these rubber bands. And the reason for that was because if I had used a timing belt pulley, I would have had to design in a precise radius for these two pulleys here and here, complete with teeth, and the distance between these two pulleys would have had to be very exact and probably determined by trial and error so that the timing belt was at the correct tension. And if any of those features were off by half a millimeter or more, the whole thing could be shot. So to free myself from those constraints, I simply used rubber bands, which I could cut and tie freely, and that is working pretty well. Now, these 3 servos, finally, are HS311 servos from Hi-Tech, and I just bought them off of Amazon. Now, finally, I want to talk about some improvements that I can make to make this project a little bit better. Most of the error is coming from the sensing stage, actually, because of the rubber band issue that I was talking about earlier. Despite my best efforts with maximizing the friction, there is some slippage between the string and the timing belt pulley if you move too quickly. So, whenever there's some slippage, the Arduino starts thinking that the string length is some length that is actually beginning to deviate from the actual length of the string. So the more you use this, the error accumulates, and basically after you've used this long enough, you can return it to the default location and the arm will be at some crazy location that is clearly incorrect. Finally, in the sphere intersection math that I mentioned earlier, there are a lot of square roots, which of course lead to the generation of imaginary numbers. And in a real physical system like this, imaginary numbers have no place, and that causes the Arduino to error out. And unfortunately, the servos then whip around to default locations of 0 degrees for all 3 of them. And I found out the hard way yesterday that this is not a pleasant result. The arm actually knocked over a water bottle and nearly short-circuited the Arduino, which was controlling it. So apparently my arm is suicidal. That was not a good idea. So anyway, that's everything. I hope you enjoyed this video, and thanks for checking it out.